All right, so here's part 2 of chapter 3. So in the last video, we talked about how waves interfere and the idea that the principle of superposition governs how they when two waves come together. You just add them together. It's really pretty simple. But the reason that that's interesting is because it actually leads to some interesting phenomena that we might not expect with light. For example, in the last video, we looked at the double slit experiment and saw that when you send light through two closely spaced, very thin slits, you actually get a really interesting interference pattern on a screen instead of just having two bands of light. And that's because light's behaving as a wave. Now, what we're going to do in this video today is what we call thin film interference. And I gotta say, it's one of the things that I really remember from general physics. I know I'm a geek, I studied physics, but I thought it was so cool to understand like why you have like the colors of light, the different colors of the rainbow on like say a water bottle if it has some oil on it, or like how a soap bubble, why does it look like the way it does? And all this is related to what we call thin film interference. So here's the picture. Forgot the picture was here, but our soap bubble looks really pretty. You see all those swirls of color. And basically what's happening is light waves are interfering constructively at different wavelengths, and that's why you're able to see that color. So this is sort of the idea of what's happening. When you have a thin film interference, first of all, you start with a thin film. So for instance, if we compare the picture on the left to the picture on the right, this material here might be water, and then this material might be oil. And so the idea of what we're dealing with here is we have some light, it comes in and it hits the surface of the top layer. Now some of that material is going to be reflected right off the top. That's ray 1. Some of the light that hits the boundary is going to go down through the thin film, that's the oil film, and it'll reflect off the top of the water and then come back out. That's ray 2. And basically, when we're talking about thin film interference, figuring out how these two light rays interfere with each other, whether they're interfering constructively or destructively, and the fact that the answer to that question will depend on what the wavelength of light is, basically leads to the patterns that we see like here. Because when we see blues or reds or yellows, it means that those wavelengths of light are interfering constructively, and that's why we are able to see them. So in order to figure out whether or not the two light rays are going to interfere constructively or destructively, we have to think about a couple things. And one of those is what will happen to a light ray when it reflects off the boundary between two different materials. Sometimes the light ray will shift, it'll undergo a phase shift, so now we're thinking of it like a wave, and sometimes it won't. So how does that work? So basically, when there's a couple rules that we want to think about. So if the light ray is going from a material where the light travels more slowly to where it travels more quickly. So for instance, in this material, the material on the left has a higher index of refraction than the material on the right. And so the way we could think of that would be like the one on the left would be like water, and the one on the right could be like air. Well, in any case, if you have a light ray that comes in and it's in a material with a higher index of refraction, reflecting off a material of a lower index of refraction, it's going to undergo no changes. It won't undergo a phase change. And so that's important to remember. And so that's sort of like a wave coming into a free boundary, like remember we did the waves whether it was inverted on reflection or not. This is like when the boundary was free and it just reflects but doesn't flip, and that's what happens in that case. However, if it goes from a material where it's traveling faster to where, and then reflects off of a material where it would travel slower, and that is the material on the left has a lower index of refraction than the material on the right. In those cases, the wave will undergo a half cycle phase shift, or we could also think of it as pi. And so basically the wave gets inverted, and that's like when we go from when the boundary between where the wave reflects off of is like a fixed boundary. And so that's really important because, for instance, when we're thinking about how the two light rays are going to interfere, we have to understand, like, has it undergone any sort of phase change, or yes or no, and then thinking about that when we try to figure out how they're going to interfere. And so this is another picture just showing that. So for instance, here is a piece of glass surrounded by air. And so when the light comes from the air and hits the glass, that reflected wave is inverted. It undergoes a phase change of pi radians, which is like half a wavelength. Think about that. A full wavelength would be 2 pi radians. But some of the light actually doesn't reflect off. Some of it goes into the material and then reflects off the bottom of the material. Now here you're going from the glass and the air, and so the air has a lower index of refraction, so at the bottom of this thin film it's not going to invert. And so what happens is then when we come up here, we have one ray which was inverted and one that wasn't. And so in the absence of the fact that this one traveled further because this has a particular thickness, these two would be out of phase, but it depends on, again, the path difference. The path difference between the two waves is going to be 2t, and then we have to compare this to the wavelength to determine what kind of interference we have. And so this is one of the situations where I find that students try to memorize the expressions, but the problem is for one scenario, a particular expression is going to give you constructive interference, but then in a different scenario, that very same expression would give you the condition for destructive interference. So I think that it's pretty useless to try to memorize which equation goes with which and try to understand exactly how you would come up with an expression. And so now I'm going to try to show you how to think that through. So let's imagine a scenario where I have 3 different materials. Here's material 1, here's material 2, and here's material 3. And what I'm going to say is that N1 is less than N2, which is less than N3. Okay, so as I go from one layer to the next, the index of refraction keeps increasing. Now, what's going to happen is I have one light ray comes into this surface, the boundary between material 1 and 2, and some of it's going to reflect off the top. Will that light ray undergo a phase shift? Well, it's reflecting off of the surface of a material of higher index of refraction, and so the answer is yes. However, there's more. Some light travels continues through into the material 2 and reflects off of the boundary between 2 and 3 and comes out. Now we have to think about now what happened when that light ray reflected off of material 3. Did that go through a phase shift? And again, because the index of refraction of 3 was higher than 2, it also underwent a phase shift. And so now these two, now the other thing we have to think about is this thin film of number 2 has a thickness we're going to call T. And so think about this. If T was equal to 0, if the thickness of that film was so small that it was basically 0, these two would be in phase. So to keep them in phase, that means they're doing the same thing at the same time. We would need the difference in the path length, which is 2t, to be equal to some multiple of the wavelength. However, it's the wavelength that it has in material 2. Because when it goes into the material 2, remember when waves go into new materials, their wavelengths changes. And so actually, that's equal to lambda over n2 for this particular scenario. And so often we'll just write this as 2nt, where, well, I guess I could call it n2, is equal to some integral multiple of the wavelength. So if I let m equals 1, that's going to be the very thinnest film, and that would be, you know, like the shortest wavelength that could be constructively interfering. This is the condition for constructive interference. And then if we wanted to have destructive interference, that's if we don't want a particular wavelength to constructively interfere. We want to get them, they were in phase, but we want to get them out of phase. And so we want the difference in the path length now to be some half wavelength, like 1/2, 3/2, etc. And although we call it the lambda sub n, it's actually lambda n sub 2. And so I get 2n2 times t is equal to m plus 1/2 times the wavelength just in a vacuum. And so this is the condition for destructive interference. So we have these two conditions for this scenario. But let's go and look at a different one. And so what if we come up with a scenario where now we have 3 layers. This is 1, this is 2, this is 3. But here, n1 is less than n2, but n2 is greater than n3. So it's not the same as it was last time. So I have the light ray coming in, and this one does undergo a phase shift. But then the light ray that goes through the thin film and reflects off the top of the third material does not. And then this is the thickness of the film. So right now, those two are out of phase, if t was equal to 0, they would destructively interfere. And so, if I wanted to have destructive interference, basically I want them to keep out of phase. So in this case, the difference in the path length has to be an integral multiple of the wavelengths, because I want to keep them out of phase as they are. So I just want to add another wavelength that'll keep them out of phase. And so 2n2t is equal to m lambda, and that's the condition in this case for destructive interference. And then for constructive interference, that's where I would be able to see a color. I want to get them in phase with each other. So that means that 2t has to be equal to m plus 1/2 lambda sub n, or 2n2t is equal to m plus 1/2 lambda. So this again is for constructive interference. So now we have these conditions, but if you go back and look at the previous slide, they're exactly opposite. And that's why I say it doesn't really pay to memorize these conditions. You're better off to be able to figure them out. And one last little slide, this is just, I thought, kind of interesting, was like how we can make an anti-reflective film is if the film has a lower index of refraction than the glass that's on top of. This is kind of like my first example. Because of the fact that both of these light rays will undergo a phase shift when they reflect off of their respective surfaces. This undergoes a phase shift, and so does this. And so we basically want to get them out of phase with each other, and so that if this thickness is just a quarter of the wavelength, then 2t is equal to 1/2 a wavelength, and we can actually get them out of phase, and it really basically stops any reflection, and so you don't have that glare. So I think this stuff is kind of cool, and it's not that bad. And that is it for Chapter 3.